Welcome, travelers, to Adventures in Security. In this video, I explore how EVPN-VXLAN works, its importance, and how to secure it. The script and study guide for this video and the references used are available in the video notes. If you like what you see, if you learned anything, please give us a thumbs up and subscribe so you don't miss further content. Network segmentation is a fundamental aspect of modern cybersecurity, essential for improving security, performance, and management within an organization's infrastructure. Traditional methods face limitations in scalability, complexity, and flexibility. So, Virtual Extensible LAN (VXLAN) technology emerges as a superior solution for network segmentation. VXLAN, coupled with Ethernet Virtual Private Network (EVPN), extends Layer 2 networks over Layer 3 infrastructures, enabling the creation of isolated virtual networks across geographically dispersed environments. This technology addresses the constraints of traditional segmentation techniques, such as VLANs, by utilizing a 24-bit VXLAN network identifier, which supports approximately 16 million unique segments. This significantly enhances scalability and allows for granular control over network traffic, reducing the risk of cyber threats spreading across the entire infrastructure. VXLAN's dynamic nature facilitates more efficient MAC address learning and distribution through its BGP-based control plane, reducing the likelihood of configuration errors and enhancing network stability. Additionally, VXLAN encapsulates Ethernet frames within UDP packets, providing seamless transmission of Ethernet traffic across IP networks and enabling flexible and scalable network designs. Implementing VXLAN for network segmentation offers several key benefits, including improved security, optimal path utilization, and enhanced regulatory compliance. As organizations increasingly adopt cloud-based services and face evolving cybersecurity challenges, VXLAN technology provides a robust framework for maintaining resilient and secure network infrastructures. This video assumes that the reader understands L2 switching and traditional VLAN technology. For a refresher or an initial understanding of these technologies, watch the videos Communication and Network Security, Part 1, Domain Separation and Segmentation, and how L2 switches use MAC addresses, the links to which are in the video notes. For a deeper look at EVPN-VXLAN and how to configure it, see the video series EVPN-VXLAN Explainer, available in the video notes. Network segmentation divides a network into smaller, isolated sections to improve security, performance, and management, controlling traffic flow, limiting access to sensitive data, and reducing the risk of cyber threats spreading across the entire infrastructure. Segmentation is essential for cybersecurity because it helps contain potential breaches. Attackers who gain access to one segment are less likely to move laterally to other critical areas. Segmentation also minimizes the attack surface by restricting access based on roles, departments, or security levels. For example, an organization may separate its finance department from general office networks or isolate IoT, Internet of Things, devices to prevent them from being used as cyber attack entry points. Segmentation also ensures that third-party support organizations for IoT operations and maintenance only have access to the devices they support, not the business network. Another key benefit is regulatory compliance. Many cybersecurity frameworks, such as PCI DSS for payment security and HIPAA for healthcare data protection, require segmentation to safeguard sensitive information. Organizations can more effectively meet these compliance standards by controlling who and what can communicate within different network zones. Segmentation improves performance because network traffic is more efficiently managed, reducing congestion and preventing unnecessary data exchanges. This can be achieved through VLANs, firewalls, or advanced technologies like microsegmentation, which enforces security policies even more granularly. One of the most common approaches is VLAN, Virtual Local Area Network Segmentation, which allows administrators to logically separate devices within the same physical network, as shown here. VLANs work at Layer 2 of the OSI model and enable traffic isolation between groups of devices, reducing broadcast domains and improving security. Subnetting, another traditional method, operates at layer 3 and divides a larger IP network into smaller subnetworks. It enforces boundaries between different network segments and enhances routing efficiency. Layer 3 switches play a significant role in network segmentation by enabling inter-VLAN routing. Unlike Layer 2 switches, which rely on MAC addresses to forward traffic, Layer 3 switches use IP addresses to make routing decisions. This method facilitates communication between different VLANs while enforcing segmentation rules. It improves performance by offloading routing functions from traditional routers and reducing bottlenecks in high-traffic environments. Firewalls are another critical component of network segmentation. By inspecting and filtering traffic based on predefined security policies, firewalls enforce access control between network segments, preventing unauthorized access to sensitive resources. Traditional firewalls operate at layers 3 and 4, filtering traffic based on IP addresses and ports, while next-generation firewalls incorporate Layer 7 application layer capabilities, allowing more granular control over traffic. Access control lists, ACLs, are also used for segmentation by defining rules that permit or deny traffic between different parts of the network. ACLs are typically implemented on routers and Layer 3 switches to restrict access based on source and destination IP addresses, protocols, and ports, adding a layer of security. Traditional network segmentation methods face several challenges in modern network environments. One significant issue is the complexity involved in configuring and maintaining these segmentation methods. As networks grow and evolve, managing VLANs and access control lists becomes increasingly cumbersome, potentially leading to misconfigurations, resulting in security vulnerabilities. Another challenge is traditional segmentation's static nature. These methods often lack the flexibility to adapt to dynamic network changes, such as adding new devices or applications. This hinders the implementation of more granular security policies and makes it difficult to protect against sophisticated threats. Traditional segmentation techniques also struggle with providing detailed access control, especially in environments with remote workers, partners, and customers. The lack of granularity in these methods can lead to over-permissive access, increasing the risk of insider threats and unauthorized access to sensitive data. Furthermore, implementing traditional segmentation in hybrid or multi-cloud environments presents additional difficulties. The reliance on hardware-based solutions such as internal firewalls and VLANs becomes less effective in these dispersed settings, leading to potential security gaps. While traditional network segmentation methods have been essential in network security, they face challenges related to complexity, inflexibility, limited access control, and adaptability to modern distributed network architectures. These limitations necessitate exploring more advanced segmentation strategies to secure contemporary networks effectively. Ethernet Virtual Private Network, EVPN combined with VXLAN, is a modern network architecture designed to enhance scalability, flexibility, and efficiency in data center and enterprise networks. EVPN serves as a control plane protocol that uses Border Gateway Protocol, BGP, to distribute MAC and IP address information, while VXLAN functions as a data plane protocol that encapsulates Layer 2 Ethernet frames within Layer 3 UDP packets, enabling the extension of Layer 2 networks over Layer 3 infrastructures. Traditional network segmentation methods, such as VLANs, face limitations in large-scale environments due to their 12-bit VLAN identifier, which supports a maximum of 4,096 unique VLANs. This constraint poses challenges in accommodating the extensive segmentation needs of modern data centers. VXLAN addresses this issue by utilizing a 24-bit VXLAN network identifier, VNI, allowing for approximately 16 million unique segments, thereby significantly enhancing scalability. Additionally, traditional Layer 2 networks often rely on protocols like Spanning Tree Protocol (STP) to prevent loops, leading to suboptimal path utilization and scalability concerns. EVPN-VXLAN mitigates these challenges by leveraging a Layer 3 underlay network, enabling more efficient routing, optimal path usage, and improved redundancy. Furthermore, the dynamic nature of EVPN's BGP-based control plane facilitates more efficient MAC address learning and distribution, reducing the likelihood of configuration errors and enhancing network stability. EVPN-VXLAN offers a robust solution to the limitations of traditional network segmentation approaches, providing enhanced scalability, flexibility, and operational efficiency, making it well-suited for the demands of contemporary data center and enterprise network environments. EVPN-VXLAN operates through distinct planes, the control plane and the data plane, constituting an overlay of an underlay network. An underlay network is the network, servers, user devices, and protocols providing the infrastructure to implement software and services supporting essential mission functions. This graphic is an example I use in this video to build a sample EVPN-VXLAN network. This example consists of a core of routers, although switches could also be used depending on the network topology. The routers are connected at this layer using the OSPF protocol and are located at 3 locations on the organization's campus. Each endpoint device is shown with its MAC address. At this point, EVPN-VXLAN is not operational. As shown in this graphic, the overlay network consists of 2 planes, the control plane and the data plane. EVPN, an extension of the BGP, uses BGP as its control plane to distribute information on the reachability of layers 2 and 3. This method efficiently learns and disseminates MAC and IP address information across the network, reducing the reliance on traditional flooding mechanisms. By leveraging BGP, EVPN ensures scalable and robust communication between network devices, enabling the efficient sharing of network and endpoint information, such as Layer 2 MAC addresses, IP prefixes, and virtual network metadata. VXLAN is the data plane, encapsulating Ethernet frames within UDP packets to extend Layer 2 networks over a Layer 3 infrastructure. Each VXLAN segment is identified by a unique VNI, allowing for the creation of isolated virtual networks. This encapsulation facilitates the seamless transmission of Ethernet traffic across IP networks, enabling flexible and scalable network designs. This network diagram shows a configured overlay for our sample network. A VTEP VXLAN tunnel endpoint is a network device that encapsulates and decapsulates VXLAN packets to enable communication between endpoints in a VXLAN-based overlay network. VTEPs bridge traditional Layer 2 networks and the VXLAN Layer 3 underlay, allowing virtualized networks to span different physical locations. In this example, our VTEPs are the routers in the underlay. Let's walk through a simple example of how EVPN-VXLANs work. Our example network has 3 VLANs across 3 geographically separated locations, as shown in this network diagram. First, S1 sends a packet to S4. Next, R1, in its VTEP role, records S1's IP MAC address information and which port it is on in its EVPN MAC address table. This is known as local learning. This is an example of a MAC address table with EVPN entries. R1 then sends the updated information to R2 and R3. Routers 2 and 3 also record the next hop to that MAC address, R1, in their EVPN tables. The learning of a MAC address and its next hop received from the local VTEP is known as remote learning. R1 looks for an entry in its EVPN table that tells it that the next hop for S4 is R3. If there is no entry for S4 in the EVPN table and the VXLAN is running in flood and learn mode, the VTEP forwards the packet to all other VTEPs in the VNI. Otherwise, the packet is dropped. In this example, R1 will send an ARP broadcast to local ports connected to VLAN 10-VNI1010 and R2 and R3. The VTEPs connected to VLAN 10 send an ARP broadcast out locally to determine the location and MAC address of the destination server. In this example, R3 determines the IP MAC address combination for S4 and sends it to R1 and R3. R1 and R2 add the information to their EVPN tables. Finally, R1, as a VTEP, encapsulates the packet and forwards it to R3. My example walkthrough is a simple look at EVPN-VXLAN to facilitate ease of explanation and understanding. This diagram shows a possible real-world implementation, where I show a spine leaf topology with the leaf devices becoming the VTEPs. Securing the segmentation created with EVP-VXLAN involves several key strategies to ensure robust protection and maintain network integrity. Like traditional VLANs, segmentation alone is not enough to secure connected resources. Additional security considerations include microsegmentation, role-based segmentation, control plane security, data plane security, network access control, and regular monitoring and auditing. Microsegmentation allows for more granular control over network traffic by creating smaller, isolated segments within the VXLAN fabric. This can be achieved using security groups and security group access control lists, which enforce tailored security policies between different segments. This approach helps control network traffic flow among application tiers and across applications, ensuring that security policies are applied only where needed. Implementing role-based segmentation using solutions like Cisco TrustSec can enhance security by defining and enforcing policies based on user roles and attributes. This method ensures that only authorized users and devices can access specific network segments, reducing the risk of unauthorized access and lateral movement within the networks. Securing the control plane is crucial for maintaining the integrity of the EVP-VXLAN architecture. This involves using BGP authentication mechanisms, such as MD5 or TCP/AO, to protect BGP sessions from unauthorized access and tampering. Additionally, implementing route filtering and prefix lists can help prevent the propagation of unauthorized or malicious routes within the network. VXLAN encapsulates Ethernet frames within UDP packets, which can be secured using IPsec to provide encryption and integrity protection for data in transit, ensuring that the encapsulated traffic remains secure even if the underlying network is compromised. Implementing network access control (NAC) solutions, such as Cisco Identity Services Engine (ISE), can help enforce security policies at the network edge. NAC ensures that only compliant and authorized devices can access the network, providing an additional layer of security for the EVPN-VXLAN segments. Continuous monitoring and auditing of network traffic and configurations are essential for maintaining security. Tools like Cisco StealthWatch can provide visibility into network traffic patterns and detect anomalies that may indicate security breaches. Regular audits of network configurations and policies can help identify and remediate potential vulnerabilities. By combining these strategies, organizations can effectively secure the segmentation created with EVPN-VXLAN, ensuring protection against cyber threats and maintaining network integrity. To summarize, the integration of EVPN-VXLAN offers a modern and scalable solution to the limitations of traditional network segmentation methods. By leveraging a BGP-based control plane and VXLAN encapsulation, organizations can achieve enhanced security, flexibility, and performance in their network environments. This approach addresses the challenges of traditional segmentation, such as complexity, static nature, and limited scalability, and provides a robust framework for future-proof network designs. Securing the segmentation created with EVPN-VXLAN is paramount, and implementing strategies like microsegmentation, role-based segmentation, control plane security, data plane security, network access control, and regular monitoring and auditing ensures comprehensive protection against cyber threats. As network demands continue to evolve, adopting EVPN-VXLAN architecture will be instrumental in maintaining resilient and secure network infrastructures. That's it for this video. Again, if you liked what you saw, please give me a thumbs up. And until next time, be careful what you click.